Hello everyone, my name is Ma Guanzhong from Faculty of Education at University of Hong Kong. In this seminar, we are going to talk about science education. In science education, we expect our students to be little scientists, to do what scientists do. So scientists are experts of asking questions. So let's start with asking you a question. So do you think you are a scientist? Okay, I think most of you don't think you are a scientist. So actually I can tell you that you can be a scientist if you can think like scientists. Because science is not only a profession, science is also a way of thinking. So in scientists always propose, develop, and evaluate knowledge claims of nature. They want to understand nature and they develop claims about nature to explain how nature works. So actually in everyday life, we also encounter a lot of claims, very messy claims. So for example, coffee prevents cancer, music enhances intelligence, and vaccination causes autism. Actually, I think we are all very confused by those messy claims. We do not know what to do and what to eat, or what not to eat, what not to do, after we read those claims. So, for example, after you read the claim, coffee prevents cancer, would you like to drink 5 cups of coffee every day to prevent cancer? Nowadays, students live in a very messy information age. They, like us, encounter a lot of messy claims in everyday life. And as educators, we want students to be literate citizens. And we expect students to be able to distinguish good from bad claims. So to achieve that educational goal, we need to understand student current performance on distinguishing good from bad claims. And basically we want to understand what kind of strategies students use in evaluating those claims and what kind of difficulties and fallacies students have in evaluating these claims. And also to teach students to be able to distinguish good from bad claims, we want to understand what kind of knowledge and understanding students need to have to be able to distinguish good from bad claims. And finally, we want to develop effective ways and approaches to teach students to be able to distinguish good from bad claims. So there might be a lot of ways to teach students to be able to distinguish good from bad claims, but which way is better? So in this seminar, I'm going to show you a potential effective way of teaching students to be able to evaluate those claims in everyday life. So there are 3 basic steps. First, we show students a knowledge claim in everyday life. For example, coffee prevents cancer. And we have students respond to that claim to express their views on the correctness of the claims. And second, we show students a set of peers' responses to this claim. And then we ask students to identify the good and bad points of those responses. And finally, because students' responses to the same claim might be different, they may have disagreements with the correctness of the same claim, then we can take this opportunity to teach students some of the key ideas about good science, what is good claim and what is bad claim in science. So what's the claim? The claim is rice differentiates good from bad. Rice differentiates good from bad. So we Chinese people believe that everything and everything in life is alive. Everything has soul. So we need to respect everything and everyone in everyday life, because if we do good or do bad things to something, then they may know we are doing bad to them. And so someone did an experiment to verify this claim. So basically the experiment is like this. So we have 2 bowls of rice, cooked rice. For 1 bowl of rice, we say that, nice, I like you. And for the other bowl of rice, we say, ugly, I hate you. And he did exactly the same thing for a month. And after the month, he observed the experimental result. So basically the result is like this. So for the 4th bowl of rice, the rice remained almost the same. There was no color change and no special odor in this rice. And for the other bowl of rice, the rice actually turned green and black. And it's also turned sour and smelly. So basically that bowl of rice went back. So you can see that the experimental result is very clear and very obvious. The experimental result supports the claim that rice can differentiate good from bad. Because the result shows that if we say good word to the rice remains almost the same. But if we say bad word to the rice turned bad. So do you believe this claim? So do you think the rice can differentiate good from bad? It's a correct claim, a scientific claim?
Absolutely not.
And so actually we collected different responses from students in mainland China and in Hong Kong. And so for example, we have this pair of responses. Student A said, no joking please, this is completely incredible. How can rice hear what we say? That's crazy. And student B says, yes, why not? The experimental results confirm it. Experiment is the golden rule of science. So basically, student A is referring to his own idea, own theory about the topic. He's suggesting that because the experimental result is different from his own theory, so that claim should be incorrect, should be wrong. And student B is referring to the experimental result. He's suggesting that because the experimental results support the claim, then the claim should be correct. So which one do you agree more, A or B?
B.
So actually we collected student responses, and some think A is better and some think B is better, so they have disagreement. So then we can take this opportunity to teach students some basic ideas about science. So actually in science, evidence is source of knowledge, and scientists refer to experimental evidence or empirical evidence to evaluate whether a claim is correct or not. And also science are very open-minded, so they entertain the possible falsehood of their own theory. They think they may be wrong or right. And when there is enough evidence that suggests some claim is incorrect, they are willing to change their mind to develop a new theory to accommodate the empirical evidence. So according to this idea, it's very clear that student B's response is better, because student B referred to the experimental result to evaluate the claim, rice differentiates good from bad. But student A ignored the empirical evidence, but simply referred to his own theory about the topic, which could be a misconception. So it is so easy to evaluate a scientific claim. So it's just scientists just need to collect evidence here and there. They do some experiments, collect some data, analyze the data, and see whether the data or evidence supports or disconfirms a particular scientific claim. So actually, it's not that easy, because otherwise scientists can live a much relaxing life. So, but what's the problem? So is there any problem in the experiment, or is the experiment is very good? So let's look at another pair of peer responses. Student A said, this is right. Experimental group versus controlled group, perfect experiment. And student B said, no, this is wrong. Bacteria cause food to go bad, and only one loaf of rice could be coincidence. So basically, student A is suggesting that anything from experiment should be good. So if the experimental results support the claim, then the claim should be correct. But student B is suggesting that actually pointing out some of the problem of the experiment. So for example, he thinks that actually it might not be what we say to the rice cause the rice to go bad, but bacteria may do that. And also, we cannot trust 112 experimental results because that result could be coincidence. So which one do you think is better? Which one do you agree more, student A or B? So actually, students again can have disagreements with student A or student B's response. Then we can teach students the idea that scientists not only evaluate the claim using the evidence, but they evaluate the evidence itself. So for example, when evaluating evidence, scientists would examine the experiment to see whether the experiment itself is problematic, or there are some weak points or designs in the experiment. So they basically look at like ideas such like control variables. They need to examine whether the experiment will control some variables that are considered to influence the outcome, because they don't want the confounding variable to influence the experimental results, because in that case the experimental results may not be trustable or very difficult to interpret. And the other idea is that the scientist wants to make sure that the experimental results can be replicable. They can replicate the results in different trials of the experiment. And that idea is related to the third one, not by chance, that scientists actually want stable experimental result rather than one trial experiment. So according to this idea, we can see that student B's response is better than student A's response, because student B is pointing out the problems of the experiment. He thinks that if the experiment itself is poorly designed, then the results from the experiment should not be very good, and we should not trust the experiment from very poor experiments to evaluate the knowledge claim. So actually, for those peer with the student responses we discussed earlier, all the students have some ideas about the topic, about whether rice can differentiate good from bad. But in reality, we have a lot of very advanced science topics about which even scientists don't know a lot about the topic. So because science are expert, and being expert means that scientists only have very rich knowledge about a very, very narrow research field. So beyond that field, even scientists don't know much about that topic. So in those situations, how can we differentiate good from bad claims in those science topics? And how can we teach students to be able to distinguish good from bad claims in a science topic about which they are not familiar with? So to answer that question, let's look at another pair of responses from students. And student A said, I believe myself. I accept the claim if it conforms my knowledge, and I reject the claim if it disconforms my knowledge. And student B said, I ask questions. Why should I believe this? What is the reason? And is the reason itself good? So I think we all agree that student B's response is better. because when he doesn't have much knowledge about the topic, he asks questions. He wants to question the claim and want to question the reasons for believing the claim. So, broadly speaking, we want to teach students to think like scientists. So we expect that when students encounter some claims in everyday life, they can always refer to empirical evidence to evaluate the claim. And also we want students not to blindly accept or reject some claim. And we want students to evaluate the evidence itself, to evaluate whether the experiment itself is well designed. So actually this speaks to the very core ideas of critical thinking or scientific reasoning. And scientists have been using this way of thinking and reasoning to develop science knowledge about nature. So we have talked about a lot about the claim rice differentiate good from bad. Rice can differentiate good from bad, and so actually this demonstrates a teaching model for teaching students to be evaluating claims and evidence in science. And for example, skipping breakfast helps lose weight. So if we teach students to evaluate that claim, we can first of all have students response. Ask students to respond to the claim, to express those their views on this claim. And secondly, we can show students a set of peer responses to this claim and ask students to identify the good and weak points of their responses. And finally, we can teach students some key criteria or ideas about good science or good claims or good quality evidence in science. And so actually although we talk about evaluating claims in everyday life, but actually this idea applies to science classroom, because in science learning, students always have a lot of misconceptions about the science topic. And then in science classroom, teachers always show students some experimental results that contradict their misconceptions about the topic. But we don't want students to blindly accept what science teachers show them. We want students to be able to critically evaluate evidence itself, to evaluate the experiments, before they use the evidence to challenge, to evaluate their misconceptions about the science topic. So after this talk, are you going to teach students to evaluate evidence? Or do you think this idea or this teaching model could contribute to students' conceptual understanding of science? So I think that's all of my talk, and I'm very happy to take comments, ideas, and questions. Thank you.